Alright guys, so today we will discuss about transformation of information. How does computers store information? So in the previous ages here, or we can say in old ages, people used to uh, store information in different ways. They used to store in a form of writings, in a form of writing in somewhere, maybe be it a stone or in a skin or just in a wood or something like that. So how does that storing of information has been transformed using computers? How we become able to store something inside a silicon chip and manipulate it using electricity. We are storing information in a form of electricity. How that has become possible, it is one of the most amazing thing to think about, I would say, when you think about how does computers store information. Have you ever thought about it? How does computers store information? Well, what is the thing inside the computers which make it possible to store information and it show us when we need something? When we instruct it to show us something, it shows us the output. How that become possible? So that's the mystery, kind of mystery for now, for you guys to unveil, to understand how that works as a computer scientist or as a software engineer or IT student. You should have these questions in your mind, that how these things work inside the computer, how the chips work, and how the memory is formed. So you need to have this question in your mind, and I would suggest that ask as many questions as you can about computers, how these things work. That's the main thing. You need to ask the questions, and once you start asking questions, you will start gathering information, be it from YouTube, be it from Google, be it from someone else. So you will get the idea. The main thing is having the desire to know about something, having the uh, mind or the questions in your mind, so that you can attract related information. Okay, so that with that being said, let's move forward. In this chapter, we will understand, or will try to understand, about common types of information that can be manipulated by computers, and why does the computer use binary numbers? Why we are not using decimal numbers? Aren't we using hexadecimals? Why is that? Aren't we using hexadecimals decimals in computer? So that's again a question. We'll answer all these things in these lectures. So stay tuned. All right. So what does the computers deal with numbers? How does the computers deal with numbers, text, pictures, sound, programs? So how does computer know all these things? That this is a picture, this is a video, this is a text, and nowadays, if you look at artificial intelligence, that is totally different dimension. You can't even imagine that a silicon chip has been able to hear, to see, to talk, can do tasks by its own, can give you a lots of information just by giving it a simple input, be it in a voice format or in a text format. That's totally amazing. So you need to be asking these questions from yourself, that how these things have been made possible by humans who once used to hunt, uh, who once were hunter and gatherers. You know how these things made possible. And here we will also learn about what type of program manipulates text. So we'll learn about these things. Okay, so what is information? First, let's define what is information. Okay, so from computer science perspective, there are 5 types of information that computers commonly manipulates. That computers can manipulate. One, numeric, then character, visual, audio, and instructional. Now, there is something which you need to understand, that when you go deep into the architecture of computer don't understand character, visual, audio, or instructions. It only understands numbers, and it understands only 0 and 1. That's it. From then on, we convert that numbers, that zeros and ones, into many kind of information, be it character, visual, audio, or instructional. So keep that in mind, okay? So first, the information must be transformed, converted into acceptable representation that computers will accept. So that acceptable representation is binary, zeros and ones, okay? So all modern computers work with a system of numbers called binary numbers, as we talked about it in the previous lecture as well. How does computers understand binary? Why they don't understand, why we don't use any other number system? Why we use zeros and one? We could use 1, 2, 3, 4, 5, 6, 7, 9, or we could use so many other numbers. But why we use binary numbers? Okay, so we talked about that in the previous lecture. Now here we will try to understand that why we use, or why it's important to use binary numbers, and what is why is that computers use binary numbers, and what is binary circuit. We'll try to understand that. Okay, so electronic device or cheapest and function most reliably if they assume two states. Okay, here is just an analogy, or just a diagram. You can see here that there is a light bulb attached with a switch and a battery. Okay, once you turn on the switch, the bulb lights up, and when you turn it off, it turns down. Okay, so that's the simple logic behind binary circuits as well. There are switches, different kind of switches. If you have already studied semiconductors and transistors in your physics class, then you understand that what is mean by switch. What is that? You might have studied the NPN or PNP transistors, the semiconductors, how the doping works, how NPN works, and how do it create a barrier for the transfer of electricity, all that thing. So if you have not studied that, I would recommend you to check that out as well. Okay, so there's a simple analogy that there's a switch which, when it's turned on, when it is on or open, it turns off the light, and when it's closed, it turns on the light. Okay, so here's a simple representation of numbers based on the light bulb which we just discussed about. So there are 3 light systems. So it has 8 possible combination. Okay, 8. You can light up 8 these things, the different sequences, in 8 possible ways. So here we could use them to indicate numbers from 1 to 7, 0 to 7, 0 to 7, which eventually become 1 to 8 or 0 to 7. Okay, so here we are using 3 binary numbers, okay, to represent the light bulbs. Now we have attached different circuits with each light bulb. If all the 3 circuits are 0, means turned off, then no light bulb would light up. It would uh, show us this thing, okay? 0, that represents a 0, which means no circuit is switched on, okay? Then we have fun. If one of the circuits is now turned on, then we have fun. If 2, then we can represent that as 101, which is in binary, it's 2. Then it would light up the number 2 bulb, okay? Then 3, if the number of bulb is if the number is 3, then it would light up 2 bulbs, 1 and 1. Here, as you can see, if there is 0, it means the switch is closed, no lights bulb up. And if in case of 1, then there is 1, so it would light up the bulb corresponding to the 1. And in case of 2, the middle bulb lights up because it corresponds to the 1 inside in the 1 binary representation, okay? And this goes on till we reach 7, which is all 3 light bulbs are light up, okay? So that's how it works. I would recommend to watch a video on YouTube where it is totally explained how these things work, okay? How the binary combination make up this kind of switching on and off of different bulbs according to the input you have according to the binary numbers, okay? So please check that out as well. All right, so here we have decimal numeration system. So it uses 10 symbols from 0 to 9. So the place value of each positions are power of 10. Numbers such as 1375, 1357 will be expanded as if the 10 raised to power 0, which represents 1. So then we have 10 raised to power 1, 2, 3, and 4, and so on, okay? So based on that, we have we can represent the 1357 in the base of 10 representation, okay? So that's how it works. In similar case, we can also use this in binary format, okay? So let's go here. Here you can see we have these numbers are 0, 1, 1, and 0, 1, okay? So we are now here, we can use this 2 raised to power 0, 2 raised to power 1, 2, 3, and 4 to represent 16, 8, 4, 2, and 1. And by the combination of these 4 numbers, we can represent any kind of number by switching on and off different different binary numbers. Like here we are switching on 1, which means we are representing 16. Here it's 0, so we are neglecting 8. Here it's 1, so we are taking 4. It's in case of 2, we are again taking 1, so this means 2 would also be added up. And lastly, 0, in case of 1, it is being neglected, okay? So these things add up to 22, which is in a decimal system, okay? So that's how binary system works. All right, so we just discussed about decimal and binary number representation. Each number has a unique representation, okay? So in binary system, we use base 10, base 2. In decimal, we use base 10. And when you when you run out of digits, make it as 0 and increment the next place value to the left. So that's how it works. Let's say if we come to the 99, or we add up to 99, then add up 1 to the digit and make increment 0 instead of the numbers. So that's how the decimal system works. In similar case, we do the same with binary numbers, okay? All right, so representation of symbols and text. To store any kind of information in computer's memory, it must first be transformed into binary numbers form. Okay, so that's the simple thing, because computers only understand binary numbers. They understand only 0 and 1. So that's why we need to transform the any number into binary. Okay, so unless until we transform that into binary, how could computer could understand anything other than binary? Okay, so that's the thing. All right, in order to translate, or in order to represent everything into binary systems, how we could we um, transform that into binary system? We usually use base 10 decimal 10. When we count something, we use base 10 all the time. Okay, but computers don't understand that, unfortunately. So there should be some way in which we could transform everything we have, be it the numbers, be it the characters, into binary code. Okay, so that's when the ASCII comes in. Okay, that's where the ASCII is needed. ASCII is American Standard Code for Information Interchange, okay, or EBCDIC, which it's a short form of Extended Binary Coded Decimal Interchange Code. So these are the two standardized set of codes for symbols. All right, these two representations help us transform or help us convert the representation of different numbers into binary numbers. Okay, so here's the list of ASCII character set. For uh, at the rate we use this, for A we use this, and for B this, and so on. So these are the representation for numbers from 0 to 9, and all the characters, all the special characters, spaces, delete, or so many other things. So that's the simple representation of ASCII characters. Okay, so that's how we convert everything into binary, and that's how our computers understands our A, B, C, and 0, 1, 2, whatever we tell it to do, whatever we have in our keyboard. That's how our computer understands it. Okay. Okay, that was about characters and numbers. Now the next thing is pictures. How do computer could understand a picture? That's again a very profound question, which you need to understand and which you need to be inquisitive enough to uh, to go deep into the logic, go deep into the logic of how does it works. Okay, so again, a picture must also be transformed into numeric form before it can be stored or manipulated by a computer. And each picture is subdivided into grid of squares called pixels. We'll discuss what is pixel later on. If the squares are small enough, we will see a reasonably good image. Okay, so here's an example. Let's say you have an image. Okay, so in image you are representing the white dots as 1, as 0, and the black dot as 1. Okay, it becomes, and when you place all these in a grid, in a matrix, if you talk in a mathematical format, then it becomes a image. Okay, that's a 2D, simple 2D image in a black and white 0, 1 representation. Okay, if you represent the black color, black as 1 and white as 0, then you can represent this kind of image is a binary format. Okay, now this is also a grayscale image of a baby. So here all it does is it has uh, divided the whole picture into rows and columns, and in each rows and small rows and column there's either 1 or 0, either 1 or 0. which make up this picture. Okay, so that's how it works. Now again, if you the photographic quality image have a grayscale. Okay, several shades between black and white are used. For level grayscale means 4 shades are used. Each pixel needs 2 bits, 0, 1. So in order to level up, or in order to improve the quality of the picture, we use grayscale, in which um, uh, each single pixel is divided into into different representation. And let's say in case of each pixels, in case of 4 grayscale, we have 4 shades are used. So in order to represent each pixel, we need 2 bits. Okay, we need 2 bits. It would be um, represented as either 0, 1, 0, 0, 0, 1, 1, 0, or 1, 1. So what it represents? It represents either 0, 0, it's totally white, light gray, 0, 1, represent dark gray, 1, 0, and represents 1, 1. So that's how the grayscale image works. Okay, if you improve that a little bit more, you can use 8-bit grayscale. Okay, you can also use that as well, so that would improve the quality of the picture. Now from that on, how you can use these pixels to represent color image. Okay, here we have a colorful image. Okay, so 3 approaches are used to display colors. Okay, first is CMYK. It uses 4 standard colors: cyan, magenta, yellow, and black. So, and then we have RGB. In modern computers or in modern systems, RGB or BGR is used extensively. We don't hear anymore about CMYK. Okay, so it uses 3 value pixel per pixel. Okay, 3 values per pixel. That could be red, green, and blue. Okay, on a computer screen. So RGB, one number given 1 pixel, that represent all the 3 colors. So here comes the representation. Here we have red, green, and blue. Now here you can see that we have a 5 to 5 5 by 5 matrix, which represents a 5 pixel image. Okay, it's a 5 pixel image, which means it has 5 rows, 5 columns representing each pixel of an image. Okay, now inside the image, we are representing in each pixel, we are representing 3 numbers: red, green, blue, with different quantities, with different pixels. Like if it is 24, it represents a lighter red. If it's more, it may represent a different color. Okay, so here you can see that there are different dimensions to it. The matrix format, we have a 5 by 5 matrix, and inside each matrix we have 5 rows and 5 columns. Okay, so in each row and column we represent different value for red, green, blue, which make up the whole image. So that's how it works. I think you might not get the full understanding of it from this, so I would recommend you to watch any video, because in videos what you get is in animated videos which totally explain this, because if we start explaining this, that would take too much time. So therefore I'm just trying to explain it as simple and just giving you the overview of how it works. Later on you could also go and watch a video solved Matt on this topic. Okay, that it's very interesting topic. You need to get the full understanding of this. Okay, all right, then we have digitizer or scanner. Is a device that used to convert an image to numbers representing a pixel from an image. That's a digitizer, which are used. Alright, then we have sound, music, or speech. how can we represent sound, music, or speech in binary format, in a computer understandable format? That's again a very interesting things to know about and to learn about. Okay, so in order to for a computer to understand each sound need to be transformed into some kind of numeric or binary format before it could be stored or manipulated by the computer. So how would that how can that be made possible? So what can be given numerical values in a piece of music? What notes are being played? What's the frequency of each note? Hertz. So yes, you know that you might have read this or studied this in your physics class, that hertz is a unit of measurement that indicates the number of cycles per second of particular sound vibration. So that's a physics kind of thing, but you need to understand that as well. So as an example, the sine of middle C is 256 hertz. Okay, the tempo of music, beat per minute, the length of the note. So these are the kind of physical stuff which you need to understand. But here we need to understand that for each frequency, we need to convert it to hertz. Hertz is the measurement is used to measure the frequency of any sound, and based on that frequency, we convert it into digital format. Okay, so representing music using MIDI. MIDI is Musical Instrument Digital Interface. It's a set of rules for connecting musical instruments and computers. Okay, it's a set of rules which connects which transform the musical instruments into computer understandable things. And musical information is sent over electronic path called channel to various instruments or computers. It tells what note to play and how long to play it and in what frequency to play it, all these things. It consists of three numbers, 144, 60, 67, 64. Tell the device to play middle C or an MDI channel at a medium velocity. And 12860 will return of middle C, the message are sent in binary format. Alright, so representation of any sound by digital recording. How a digital record convert a sound which is just vibrations in the air. Okay, how does a digital device convert that vibration in the air into digital format? So the sound is being divided into tiny segments. When a device hears some or a vibration hits the membrane of the mic, it divides into different segments and store it in binary numbers. The computer transforms these binary numbers in and reproduce the voltage, and computers transform this and produces a voltage corresponding to each number, and these voltages are sent down to speaker wires to produce sound. So that's how it works. Alright, so representing speech, human speech is being digitized, and how it's most possible. So computer can create human speech. Nowadays you could see computers could produce not just your image, but your voice as well. They can synthesize your image, your picture, your video, and your voice. You won't be able to understand yourself. It has gone that much far in synthesizing uh, different digital assets. So, speech synthesis, the process of producing human speech by creating the right frequencies of sound in the correct timing so as to mimic human speech. Alright, so problems with digitizing whole word. Now, how it's it's very interesting that whenever we are digitizing whole world, it becomes very difficult because a human can computers cannot digitize an analog signal. It needs to be digitized in some discrete way. So therefore, we need to convert the speech into different segments, parts. Okay, so the real rule of human speech requirement different versions of the same word, questions, comma, period, and so many other things. So in order to convert this, what we can do, human language can be broken down into smaller number of sounds. Like when I'm talking, there are different segments of sound which I am um, making, and when you hear them, you understand them. So these sounds, this different type of sound, these different pitch of sound can be converted based on different meaning to each of them. All right. So phonemes are the fundamental sound of any given language. There are various uh, phonemes which varies from language to language. For example, the Hawaiian language has 12 phonemes. Now, if we come to Pacific Northwest Indian languages, there are over 100 phonemes. Here we will see how this phoneme works. For example, let's see that E as in bee, I in mitten, E as in make, E in let, E as in head. So these things are called phonemes. Okay, for example, P for if we come to consonants, we have P, T, K, F, C, She, chest, R for rate, Y, yet, and so many other things. So these are the simple phonemes of American English. Okay, now we can convert these things into digital format easily, more than any analog signal directly. Okay, so therefore these are divided into different phonemes in order to digitize them. So constructing natural sounding words and phrases. Phonemes are of particular language are chosen. They are chosen, and binary numbers are assigned to each phonemes. For example, let's say phi. We assign a different binary number to this phi, and three additional factors have an effect on how words, phrase sounds. Inflection, which involves the rising or falling or pattern of pitch on individual phonemes. For example, when I'm talking about something, how does the pitch of my sound goes up and down based on what I'm talking about. Okay, so that's what we call the inflection, which changed how a word phrase sounds. Then we have duration. What's the duration of sounding any phonemes? It affects the particular way word sounds. Then elision, which is a connection of two or more phonemes sliced together so that when one ends, the next begins. For example, when I'm talking about something, when one phoneme ends, I take that with the next one. How that works? We use elision, which is the connection of two or more sliced together phonemes. Okay. Oh, so instructions. Next thing is we talked about sounds, how sound is synthesized and how sound is digitized. Okay, I think you might get the idea that sound is divided into different phonemes, and they for each phonemes are different binary numbers assigned to them. And when we're synthesizing, we use that phonemes, and inside to synthesize any video, we use either inflection, elision, or there's a duration based on which we can synthesize any kind of audio. Okay, that's how it works. Then we have instructions. Instructions are imperative that means they command some action. Each instruction must be clearly understood by its intended receiver. There must be someone who understands the intentions behind the instruction. and the information needed to process the instruction must readily available. And for example, automobiles fasten seatbelt command, highway patrol officer pull over command, cooking recipe makes ingredient thoroughly instructions. So there are lots of instructions um, which could which are imperative and which command an action. Alright, so a computer instruction must be in a similar way, like instructions which we talk about that fasten your seatbelt, or let's say a patrol officer asking to stop the car or something else. The computer instruction must also be stored in a binary format, and whenever those instructions are being called, and that means we are instructing the computer to perform some action. Okay, so within the computer, before they're being used, we need to store them, and for storing them, we need to write them in a particular format. Okay, now here comes the program. Program is basically an instruction. Okay, keep that in mind. Programs is basically an instruction. It is a collection of list of commands designed for computer to follow, which gives some desired result. Okay, so now here is the main questions which you need to ask yourself: that how does the computer understand any programming language? Okay, now if we talk about the high level programming languages like Java, C++, Python, JavaScript. Now, how does the computer understand the Java, C++, or Python, convert that into assembly language, and that assembly language is a kind of instruction, a distinct instruction, which is then being executed by the computer, okay, to give us the desired result. How that works, you need to understand that. And as a computer scientist or a software engineer, whenever you're studying introduction to computer, keep these questions in your mind. You need to have these questions in your mind, that how these things work, because when you go up in the next level or in your next semester, when you study the higher level concepts, you will get the idea and you will come closer to the conclusion of understanding how these things work, how the computer understands the programs. Okay, so keep these questions in your mind, different questions regarding how these things work, how the computer understands, how the computer stores information, how it shows us something whenever we ask it to, we instruct it to do something. So keep those questions in your mind, because whenever you uh, go on to next levels and you study different subjects, like you will study Java, Python, or any other programming language, and how that works. Then you would also learn about digital logic and design, that would essentially make you understand that how computer memory works, and how it is being built, or how any digital circuit is built. So that's just extra thing which you need to understand. Okay, so representing the instructions of program word hunt. The purpose is to understand how a series of instructions can be stored in a computer as a group of binary numbers. Okay, so that's we have different words or commands. Now, how does these instructions can be stored in the computer as a group of binary numbers? Instructions are the predetermined list of commands that comprise all the possible instructions needed to perform a particular task. So instruction sets are predetermined list of commands or instructions that are commands that consist of all possible instructions in order to perform a particular task. You would understand this, how does that this line means that instruction set is the predetermined list of commands that comprise all of the possible instructions needed to perform a particular task. Okay, so for example, here in the SADC format, we have action and object. Action, the verb that tells what you do. In simple English, if you look at that, the verb tells you what to do. Object modifies the verb telling where, how much, and what the verb requires. Okay, In similar ways, if you if you look at the way computer programs work, if we here go to, then you might go to some page, select, you need to select from this line and that, counting down from line 1, counting the designated line number, forward, count the number of words designated to the right, back updating the word immediately, and so on. Now we or these are the words, okay? So go to select, forward, back up, right. We just discussed about them, that these are the different words. Now we are representing them as programs in decimal format. If we represent all these instructions in a form of decimal numbers, that would represent 1, 2, 3, 4 up to whatever you want to do, and then you could represent that in binary numbers. So essentially, we are representing different numbers in binary format. For example, for go to we have 001, for select we have 010, and so on. Okay. Two man the difference between our word hunt program and computer program. The computer programs, so we just talking about a general analogy of how the word hunt program works. Now, how does computer program works in real world? There are two main differences, which is that the computer programs would have originally been written in programming language that then be translated into binary numbers. Computer programs or would be translated into binary code numbers. So there is a whole process of you would learn about compiler construction. In the compiler construction subject or class, you would learn about how these computer programs are converted into binary numbers, or simply assembly language, and then assembly language is being converted into binary numbers. So you learn about that later on, and each instructions in the instruction set would have to be something that the computer was capable of doing. So each instructions inside the computer or in whatever you're writing in a programming language should be set of instructions that the computer can execute, that the computer can actually understand. And if you write something else which the computer don't understand, it would give you an error. Okay. All right. Even though instructions as differ, they all contain these classes of instruction: arithmetic instruction, data movement instruction, logical or comparison instruction, control instruction, input output instructions. In any computer instruction, be it in assembly language or something else, we are doing these classes. We have all these classes of instructions. We have arithmetic instruction, data movement, move this data from this place to this place, or move this data from this memory space to this memory space. Logical or comparison instruction, compare this number, let's say this is 2, 3, compare these two with each other and give me the result. Control instructions, we control how the instructions, in which way the control instruction would be executed. That's control instruction. And then we have input output instruction, which just simply either instruct the computer to take input or give output of something. If you'd learn these things about these things in detail and in your assembly language course or computer organization and assembly language, which is one of the most fundamental courses, I would say you must pay attention to and understand it in details. Try to make it understand in details, okay? All right. So our instructions, every instruction must have two things: opcode and operands. Okay, these are the two main things which every instruction must have. Now with opcode, the part of instruction that tells the computer what to do. Okay, it tells the computer what to do, and the operand are just numbers. Operands are the object of the operation can be performed. Example: if the operation is to add a number, then the operator will tell where to find the number, date is to be added. Okay, now here's the thing. The opcode tells the computer that choose this instruction. Okay, choose this and do this. It tells the computer to do this, while the operands, it represents the space. It tells the computer that there is this number and there's this number. Now you have to perform this instruction from the opcode on this number. So that is how the opcode operand combination works. All right. How can the computer tell what this string of binary numbers is used for? An instruction, a number, a sound frequency, the value of the pixel in grayscale image, or an scale character. How can the computer tell what this string of binary even means? It is just 0, 1, 0, 1, 0, and 1, 0. It don't really understand what it actually is. How could it understand? It could be instruction, could be number, could be sound frequency, could be anything. Okay, it is the program that is active that determines the interpretation of the string of binary numbers. It is the program inside the computer that determines that what does these things means. For example, now we talked about how does why we use binary numbers instead of decimals, and how binary numbers are converted into decimals. Then we talked about different instructions. We talked about how different representation of numbers or different representation of informations in a visual number, character, or whatever form. We talked about ASCII code. Now we are going in a progressive way towards understanding why how does an information is processed. Okay, so we talked about how does the information, what are the type of information, how does computer convert any analog or any signals into digital format or binary format, and then how does computer understand the binary format. Then we come to this part where we talked about how opcode and operand works, that opcode tells what instruction to perform and operands tells where the uh, object or where the value is to perform instruction on. Okay, next thing is the application. Okay, it is the application software. Now next thing is how does the computer would understand any kind of binary number. It would get a lot of binary numbers. How would it understand that this is actually what I need to do with this number and this is actually the number is? Okay, so then comes the software application. The application tells that if you get this set of instruction, this means you have to do this thing. Okay, for example, we have word processor. It has replaced so many things. Like Microsoft, we lately nowadays we use Microsoft, right? Microsoft Word. So it has replaced so many things. Typewriters once used to be very wonderful invention of humans to write anything, but nowadays nobody use typewriters. We all use um, Microsoft Words and printer and these sort of things. So it have two major categories of function. Text entry, just we write something, entry text, allow you to type or edit document, and document format allow to determine the appearance of the document. So this is the major categories of functions which we can see in any word processing applications. So then we have text entry features, word automatic return that causes input to go to the next line when it reaches right margin, and cut and paste, selecting Word document, undo, redo, find and replace, spelling and grammar. So this are some of the features of any word processing application. And there are formatting features, let's say serif hooks, I think you might have better understanding about this, that what these different font styles and different things are. It's, I think, not really necessary to talk about, and there's not much to talk about. Why our word processor needed? That's the main thing. Why we need them? We need them because much of what we do is committed to paper or electronic format. Nowadays, it's all electronic format. If you are doing your assignment, it's all in digital format. You just write in a Word document and just you submit it to your professor or your instructor. The appearance of your document is often the first impression of you. Or let's say if you are sending your resume to someone, you write in a form of document and you send it. That's an impression of you. Or multiple copies could be created easily. That's what we need for process. Well, all right. What's minimal function must a word processor have? So these are some of the minimal functions which word processors have: easy enter text, moving segments, converted documents, and setting margins, changing styles, and all that stuff. What types of support program are available to enhance word processor use? Do spelling grammar, spelling checker, and all these things. Publishing programs, type manager, clip art, talk program, document review. So these are the support programs in any word processors. Okay, is the special support hardware available? Yeah, we have different printers and for making the hard copy of or you know a special of our word process documents. So that's come to the end of this lecture. So in this lecture, I tried to make it possible for you to understand that why we use binary numbers, then how does binary representation works, and then what are ASCII codes, why do we need ASCII code, and after that, uh, how does numbers are represented in different formats, like how does computer why does computer understand how does computer understand different binary format like image, how does it understand image, how does it instead recognize sound, how does it understands different other things. And then we uh, uh, discussed about how does computer understand different instructions. Essentially, when we write something or we click on something, we are instructing the computer to do something. How does computer understand all these instructions? So then comes the opcode, which are basically a combination of objects and instruction code, which is opcode, which tells the computer that you need to perform this instruction upon this value, which is placed in this address. So that's what opcode and operands are. And then we talked about what are the different applications, why we use the application, why we need an application. So an application is something which makes sense of a binary string. Okay, so how would the computer understand that? What does that this binary string means? That's where the applications comes in. They make the computer understand that uh, I'm giving you this string. That means you need to perform this action on this stuff. Okay, so that's how these things work, and we discuss about word processors and different features and all this non-essential stuff which are redundant, totally redundant. So that's how it works, and that's all for this lecture. See you in the next one. Till then, keep learning, keep asking questions, and don't rely on one source, and explore as many sources as you can, but try to understand things by your own. Okay, so that's all. Thank you.